Get going. We're standing at the final lecture of the week, and that of the module of this course specifically focused on networks. Networks as important mediators of interactions, networks as outcomes of affiliative interactions, networks as emergent from movement, mobility patterns, and resource seeking, service seeking, and networks as tied in, both as symptom and cause of many types of health behavior, an influence on health behavior, and a reflection often of health knowledge, attitudes, beliefs, needs, etc. Today we're dealing with the third component of this, which is going to focus on dynamic networks. And to that end, I've uploaded to the course sites a set of 4 models, I believe it is here, each of which includes different perspectives on, depictions of, and characterizations of drivers for, and in some cases, impacts of dynamic networks. We may loop back to address some of these. I do want to feature them in Cameo as time allows, but I also want to make sure we can do justice to some of the conceptual material I'd like to present. I want to highlight first that there's a model called, it's a bit of a mouthful as the norm, minimalist network ABM model with network dynamics using Logic 8 version 4. What it lacks in brevity, it makes up for in specificity. This is a model which I'll be posting some additional versions because it requires some further refinement for the current version of AnyLogic. But it does involve infection transmission over a dynamic network where people's are forming and breaking partnership connections with others. And there's a variety of scenarios which are designed to try to depict situations where there are dyadic networks, where people are meant to be connected, or triadic networks, where one person tends to be connected with others. And there's some issues with running it on this version of AnyLogic. I wouldn't take it quite too seriously here, but if you're interested in understanding some of the mechanics of networks and some of the considerations that come in and when modeling partner change, this might be an interesting model to look at. And we'll turn to some other such models posted as well within coming minutes. By way of introduction, we've been dealing, except for yesterday's lab session, where we built up a network with mobility and we had dynamic networks, with that too being posted from yesterday and the video being posted. We've been predominantly focusing on static networks. And static structures are rather common for as representations of networks in agent-based modeling. But we need to bear in mind that relational attributes, just like other attributes of a person, for example, their infection status or aspects of their beliefs or aspects of their vaccination status. There are things that can evolve, and we can have evolving connections. And indeed, Churchill once said, famously about social housing, we build our housing and then our housing builds us. We build our buildings, I think is what he said, and our buildings build us. Reflecting the reciprocal relationship of the built environment, something we build on shaping our lives. And the same thing is true, arguably even in a more profound and ubiquitous way with networks, right? We build our networks. Often they are shaped, I should say, our networks. They're often shaped by affiliation, sometimes by homophily, seeking out people with whom we feel some bond of kinship or comfort or attraction or being a fellow traveler. And then our networks build us, right? Perhaps we affiliate with other vapors who could give us cartridges if we're out, and they shape our friendship networks and mean that a lot of our relationships and friendships are with others, people who vape. The same thing could be said for smoking, right? Same thing could be said for people who go to an exercise facility to work out, meet others there, they become part of their social networks, and that builds their sense of community and their likelihood of persisting in their exercise habits. Same thing with walking groups, right? So when we represent networks, it behooves us to reflect that while static networks can exist, and while we might characterize certain networks, say familial networks, as largely static, there's many types of networks that are dynamic. There's many types of persistent interactions characterized as networks, even with family members, that are dynamic, right? A proximity network. Remember, I reminded people 1 or 2 lectures ago that there's nothing given and canonical about the idea of a network connection. It's not like there's only one possible type of network connection. You have connections of many different sorts. They represent some sort of persistent route of interaction. But for example, with family members, we may be proximate to certain family members and then no longer proximate to them, and there's a dynamic network. And a static structure has material bearing, often profound bearing, on the dynamics over that network. We saw 2 days ago and then on Monday, got a glimpse of it as well, a sort of preview of it, that network are aspects of model structure, and they exhibit structure that's part of model structure, and they affect behavior often in very important ways. And whether it's contagion or spread of innovation or spread of conspiracy theories or rumors or what have you, the structure of networks can limit possibilities, and static structures can really limit possibilities of, say, infection spread. Had that model we built yesterday of people circulating among homes and workplaces, had they just stayed at home, the initial infected person could have infected a few people in their home, but it wouldn't have spread between homes, right? And because given one home, they would have spread it to others in that home, and then it would have potentially ripped through that home, but then died out. But instead, they were circulating to workplaces, and those workplaces were cohabited during the day by people from other households who brought it home to households, and it connected, right? The presence of network dynamics adds additional freedom in the spread of connection. It can allow for connecting transiently separated components, components that you wouldn't think are connected but are indirectly connected. They're connected for a defined part. Even if we have person A, person B, and person C, person A can spread infection to person C, even though at any one time, mark my words, at any one time, there may be never a connection from A to B and B to C. It could spread from A to B by having first a connection from A to B that allows it to spread to B, and then a connection from B to C that allows it to spread from B to C. And the net effect is a spread from A to C without there ever being a contiguous path, right? There's a temporal path we might think about that goes beyond a reductive property of being just defined by a sequence of connections all there at the same time. So this notion of network change is an important one. We need to bear in mind it's sort of the speed of network change relative to the evolution of a person is important. If we're dealing with network change, which only takes place over time frames vastly longer than our focus, maybe we're focused on the outbreak of measles in a care home, and it's true people arrive at the care home and leave the care home over the multi-month time frame, but for all intents and purposes, within these couple days, it may be that we just view it as static connections between them. I won't dwell on that more, but whether you characterize it as a dynamic or static network does depend a little bit on your time frame and the relative time frame of other dynamics in the model versus this. Now, time is short, and I don't have too much time with these slides. And once again, we find ourselves with a lot of material to cover. I will say that if you're contemplating a model seeking to investigate the impact of interventions, network dynamics, like characterizing dynamics in networks, will often be, not always, but it will often be a part. Many interventions work through network dynamics. If you want to simulate over time the effects of isolation and quarantine measures, people staying at home, right, instead of circulating, being in isolation, or quarantining themselves after exposure just in case they're infected, as distinguished from isolation of a known infected person. Needle exchange programs, perhaps sharing needles in a given session as an aspect of connection, but having needle exchange will reduce the number of shared needles and therefore the number of connections between people by which bloodborne infection could pass from person A to person B. Participation in support groups, I alluded to it earlier, walking groups, right? For physical activity, but you could argue this for mental health, support groups, groups that come together to talk about about challenges people are going through in their lives, talk it through. For substance use, right? Having an accountability partner, someone who's with you and can sort of hold you to account when you don't live up to your goals or your commitments. Using that as a strategy to build your likelihood of delivering on your commitments by having someone present for that time. You might be interested in investigating the impact of that, of forming accountability partnerships during the model operation. This is what, and I could list others, right? Support animals, paraconsumption, I'd mentioned, supervised consumption sites, etc. So why do we see network dynamics? Well, there's many reasons, right? There's many particular mechanisms that word again. Many causal mechanisms by which network undergo change, right? We can have at the arguably the most coarse level, people joining and leaving a population, right? A baby comes into the world and it has a social support network and a set of connections. In most cases. There can be change in relationships and partnerships, right? Not all relationships are permanent, for better or for worse. There can be intentional agent behavior, including in breaking partnerships, but people seek others out, maybe from shared demographics, shared language, shared knowledge, attitudes, beliefs, right? People seek services and resources and come into contact through that. They seek shelter in a homeless shelter. They need to go to the food bank, right? They come to a class. They gather for various reasons. That brings their network into being. And whilst they're there, they may be subject to certain benefits of that network and certain risks in terms of spread of ideas, innovation, knowledge, or in terms of infection, misinformation, spread of rumors, adverse rumors, etc. People accumulate social capital. People seek out connections to have connections that they can exploit, right? From which they can secure advantage. And finally, I'll emphasize, and we saw it yesterday, those of us who are staying there through the session, mobility can induce network change, right? The fact that people move back and forth between homes and workplaces changes their networks that are paying around them and their exposure. If you'd like a little bit of an example, I'll point you to one that I have posted. It's communicable mobility 3 with networks. Okay. And here we'll if we go open it up, and I recognize some of you will download it. I'll give just a minute. But once we open it, we're going to run the medium population scenario. And what we're going to see is a bunch of agents, but the agents are going to be engaged in mobility, and whilst proximate to each other, while they're live within a certain distance, they'll be connected. And if an infected agent is proximate, that is connected to a susceptible agent, that susceptible agent will be at risk of securing, of contracting that infection. So what was initially, right, here, and I'll slow this down so we can maybe see it from the get-go here, right? Here we have one initial index infected. This is patient 0, right? And how many people could they infect if the networks were static? How many could they infect? Directly and indirectly. In my screen. 4, right? It's the connected component, right? Homology group 0. Okay. Okay. So it does spread to those 4, but those 4 start to spread now. They're moving around, right? And by virtue of moving, they can come into contact with others. They can spread the infection. And the infection starts moving across the network in ways that would have been utterly impossible because they were in separate components without the mobility, right? And what we see is it diffusing across the network actually with shocking speed. In a population of 200, we see it reach a prevalence, right, of those currently infected of approximately half the network, right? And then it started to come down. I think the point, though, is clear, right? This is a case that is very visually evocative in the sense that it's very obvious to see that the infection spreads far faster because of mobility, far further because of mobility, right? Mobility makes this infection spread. It's not that it can't spread without mobility. It can in a very localized way, but it's the very to spread so far and so fast and so fearsomely effectively. All right. Okay. I will draw on another if I could, and I do so with some trepidation because I really do want to cover some important additional understanding. I'm going to open up a model called hierarchical infection transmission. Mumble. It is hierarchical infection transmission V11 any logic 8. Okay. I'm going to run this model just to give you some sense of what it involves, and you can explore it. Here we have 5 cities, each with some initial population, and this is a hierarchical model, hence its name. And so we have city agents, 5 of which are shown. They are in a network, but within each of those city networks is in turn, if we go click on this, excuse me, I'll have to do it in this here. If we go over here, oh no, it did. Yes, it opened it up. Here I've sort of looked at one of the cities. City 1 has a population of people of 284 people, and they are wired up, as you can surmise from these little connections. Those are individuals, right? Within the city, nested in the city. City 2 has 344. It has some agency. It can perform an intervention, and people are connected up there. City, here's the third city, number at index 2. And this one is already infected. There's some people infected. Those others, city 1 or city at index 2 or index 2 was actually infected as well. Okay, index 1 is not infected, hence it's not red. But here I will emphasize that cities can take action, and they take action by virtue of their. I use this little home icon to zoom up. They can take action by virtue of their local prevalence. So this one is infected, and I think I'd have to check, but I believe the red around it actually means that an intervention is in place. But what's really notable here is that it's not just that you have these cities and they can be infected within a city. It's the fact that we can have people move between cities. So people move and they bring their infection status, right? So if someone who's recovered is which I think is what's indicated here by this magenta, if indeed that's the name for it, color, they won't bring the infection with them. But if someone's infective, if it's spreading in that home city and they bring that infection with them, they can infect people in other cities. It looks like here it may have recovered without spreading it. So I'm going to stop this run that was a chance sort of event, as often happens with agent-based models. We see different outcomes, and when I'm running it 1,000 times too faster than I want to. Sorry, I'm going to go back to speed 1. I'm going to restart it. And what you'll find is that if you run this at a modest speed, the initial infective if they move infection before they recover, they can bring it. But whoever they infect could also move and bring the infection, right? So here we have it running, and here's an infective here. It's spread to 2 people, but it doesn't look like any of the infectives. This looks to me like a exposed person. So they've come without knowing often that they're infected. They're latently infected, so they may also be in a incubation period. And as time proceeds, they may infect others at this new location. It looks like the infection is spread here. And so once again, mobility between environments has spread infection, much as you might imagine a plane with one infected person could bring an infection across the Atlantic Ocean from, Toronto to over to London, right? And disseminate the infection in a new country. Okay, so that shows an aspect of mobility kind of at the city level. In the interest of time, I'm actually not going to show the final such model right now that I've packed up, although you're welcome to look at it. You'll find it very reminiscent of what we built together. Those of us who joined me for the lab yesterday, where agents move between locations like school and home or workplaces, et cetera, and where infection can take place. They can bring infection, they can spread, and where interventions might shape the ability for the infection to spread by, for example, having people work from home or having people, encouraging people to lower their community circulation, avoid gatherings in a community, or having schools closed where it's possible, or other types of interventions. Now, I hope my remarks on these things, both the ubiquity of network dynamics and the impact on underlying dynamics of a model, the induced dynamics, has persuaded you that there are some contexts in which characterizing mobility and characterizing network dynamics are important. I do want to emphasize that if you're seeking to build up a model that incorporates network dynamics, there's increasing opportunities with big data collection from smartphones, certain types of wearables, Bluetooth beacons, et cetera. Opportunities to gather information on network dynamics that can give us understanding of some of these patterns that were unthinkably burdensome to imagine collecting in the past. We've certainly done a tremendous amount of work with that with our Avicenna research program, and studied, for example, with a given participant, their circulation in different environments during working hours and after working hours, finding that in many cases there were distinct patterns of circulation for their after working hours circulation, such as down here on Broadway, versus during working hours. You could also look at, a weekday, weekend. And using Bluetooth connections, for example, we've, tracked contact patterns at a 5-minute level of granularity, but also summarize them up to things like weeks. So here's context in one of our studies from, 15 years ago. One of our shed studies, I believe, or it may have been a flu-based study with H1N1 in 2009. And we have participants numbered. And one thing you'll find is like, here's participant 4. They're very tightly connected in week 1 to a set of participants like 35, 24, 38, 12, 33. Or better yet, because it's so pronounced, 2, 9, and 33. Very strong connections. These are kind of weighted connections, with thicker meaning a stronger weight. They exhibited long periods together, 2, 9, and 33. By contrast, whilst you can find some of those here, like 3, 3 is no longer 2, 9, and 33. I stand rather sit connection. Here's 9. Here's 2. 33 is over here, but does not have a particularly strong connection in that week with 9. Just a more minor one, right? 16 and 30, perhaps here you could try to figure out if 16 and 30 are connected in week 2. There's no guarantee that their networks will preserve that. And in fact, with some of these, the changes are quite significant. 16 and 30 are, in this case, more or less preserved. So, a lot of our work, we've done it, and a lot of our use of ABMs in this context with dynamic networks have been driven by empirical data collection, recording proximity of individuals to each other, and using that information on those dynamic networks to drive agent-based models. And what I show here is a depiction of 2 ways of deriving at a given time interval of others in this case, in a study, which of them were proximate to the red individual. And one route is via Bluetooth beacons, a technology which, I don't think needs elaboration for those present, but is often used for operational tasks like connecting to headphones or connecting to, devices in your home, from stoves to treadmills and refrigerators these days. Here you're using the received signal strength indicator, which indicates the strength of a Bluetooth connection from a given device, and we're thresholding to require the strength to be at least some measure of strength or stronger. And that's what's going on here. By contrast, with GPS, we could characterize the locations of individuals, in this case, again, participants, and characterize, by extension, those posit that a set of them are in proximity if their measured position relative to each other lies within a certain margin of error. So here we might estimate that these 2 individuals, for example, are 4 meters apart and count them as connected. These 2 might be judged as 9 meters apart, and they're considered not connected. But these are considered connected. Now, what's shown here, though, is that because of GPS error, because of the fact that routinely GPS includes error that is actually built into the system for privacy, but also for military reasons of limiting accuracy of, missiles and other military hardware, the error may misattribute one person as being near another, one participant as being near another, and give the misimpression that two lie within a certain proximity. Now, if one thinks about that sort of sensing, if you're sensing proximity based on Bluetooth, these are the left two columns, or based on GPS, the right two columns, and with each characterizing some sort of threshold. Here we require people to have a particularly strong signal strength. Here we have a less strong threshold for signal strength. More people will tend to be connected here. If we consider it with a low signal strength threshold or low requirement for signal strength for two people to be, excuse me, a strong one. So here we're requiring a very strong Bluetooth signal, here a less strong. There's going to be fewer people connected if we require a strong one, right? We're requiring something that is more demanding, that's more exacting. Same thing with GPS, right? If we insist that people lie within a certain strength of them, and by extension, that the criteria for being proximate is more demanding, we'll have fewer imputed connections than if we have a relaxed one. Each row here represents a different study. So this is the SHED 7 study, the SHED 8 study, the SHED 9 study. These are sets of studies that we ran about 10 to 15 years ago with different participants. And here we're inferring contacts over some period of time and coloring by sort of the weight, how much of their time together was, how much time they spent relative to others. So for example, these two, we consider high weight. If we have more relaxed GPS criteria to be considered, require less proximity, less tight proximity. Here, those same two people are in connection. And we had a whole research program of studying the degree to which you could be forgiven as thinking this diagram commutes. Each way it should give, the degree to which it gives similar outcomes. If we have full resolution sensor data and we aggregate it up in time, so all we do is we have data on people's connections every 5 minutes, and instead we aggregate it up so they have one network per day, or even more so, one network for the entire study, say weighted. And then we have a simulation model that simulates the spread of infection over that, and we get some outcome, right, from that. Versus if we take the full resolution sensor data, we have some agent-based transmission model, we get some outcomes, we compare the outcomes. What was the simulation model giving on a very aggregated, temporally aggregated network, like a static network for the entire study, just one static network, weighted perhaps for more accuracy, or potentially unweighted? To what degree do we get similar findings for a temporally fine-grained network where it's changing every 5 minutes? And we have the luxury of doing that because we can measure these things. And our smartphone-based Avicenna data collection system that came out of our lab with a neighboring lab here in the Department of Computer Science could give us that ability to characterize that. And that's what we did starting in 2009, and with these many studies since then. And without dwelling overly long on it, I'll just note that We examined this in a set of studies over the years, and we found that if you're studying infection transmission at the most basic level, and this was a paper from 2012, so getting close to 15 years ago now, 14 years ago or so. If we simulated the network at fully detailed level and we characterized the sort of the number of infections that occurred in the model at a fully detailed level, where these networks were changing every 5 minutes, versus if we had a fully aggregated network, right? One where it's the same for the entire study. We just consider people as always being in the same network. The network is fixed, and they can transmit at any time across that network. There's no change in the connections. That actually approximately doubled the number of infections that you would think would occur. And we had various approximation schemes. We examined the assumption of treating picking out certain days and treating them as typical, like only measuring it, as was the practice for some studies at that time, measuring one day and saying that's the typical day of a high school student. Now we'll simulate infection spread across that for a much longer period and taking that as like a typical day, thinking, schedules are precise enough that, regular enough that would give a good understanding of how infection would spread over, high school over many days. It turns out you have high variability in the results, and it tends to much overstate what you could get by characterizing at a very detailed level every 5 minutes, for example, people's contact patterns. That's what the full detail. I think in this study it was actually every 3 minutes, if memory serves me. This is a small world network. Some of you may remember the small world network, but where we fitted it to a certain distribution, and we had a very nice fit, but it way overstated the amount of infection transmission. And we did many investigations of this. So we examined the impact of, in this paper, positing that we'll have a typical weekday and a typical weekend, and asking, if we did that for all these different days in the study, we had one weekday and one weekend, one distinct pair of that, how much variability would we get in terms of how many infections we'd expect to occur? And the answer is it was highly variable, right? Like which day you pick as representative for weekday and weekend really make a difference. And it can make a difference by many times over in how things spread. This is the maximum temporal resolution. There's some variability here just due to chance. Sometimes it's more, sometimes it's less. But I think we only showed the mean one here, but this is the variability. But you can see it's dwarfed by the variability of positing that this pair is representative of the whole of weekdays and then weekends, respectively. This is the aggregated, weighted graph where we just aggregate the whole thing together, treat people as just having contact patterns in a static way, a fixed way, with each person is with a fixed set of people for the entire study. Way overstated how much you could spread, because there's in the detailed transmission, maybe there's person A, person B, and who are sometimes in contact, and person B and person C who are sometimes in contact, right? And if person A contacts person B first, and there could be transmission, and then later, mark my words, B contacts C, then that could lead to that infection which came from A to get to C. But if that occurs in the opposite order, B contacts C first, and then A and B contacts B, that would not allow that transmission to occur to C. The order is wrong, right? Even though it doesn't require at any one time there to be a connection from A to B and B to C, it has to be in the right sequence. There has to be a temporal path in the sense of bumpus et al., I might add, from A to C. And hence, if you just aggregate together, you say, well, if A ever contacted B, we'll consider them connected statically. Well, they're going to have a connection in the static graph, right? It's a connection. And B contacted C, we'll have a static connection. Maybe it's a weighted connection. We consider them as having been connected 10% of the time or something like that. To in fact C. You don't get this issue of it's occurring in the wrong order, therefore it can't. In fact, that's some of the gist. I would note that, for those interested in it, if you measure these things with Bluetooth versus GPS, you get quite different distributions of contact times. So you consider, you perceive people, a pair of people, as being in proximity for a longer time if you use GPS to judge whether they're in proximity. The signal is less precise. So perhaps at a fine-grained level, they're actually quite far from each other across a large lab, for example. They're in quite different areas of a long lineup for a bus or in a bus station, they're in different areas of the bus station or a long lineup at Tim Hortons or whatever. But if you're measuring with GPS, it's coarse enough, you say, oh, they're in proximity. And they're in proximity for longer, you think. Whereas with Bluetooth, you can actually recognize, this is even, can't remember the formal title for an inverse cumulative distribution function, right? How many spend that much time in proximity before it's stopping? Here, with Bluetooth, most connections seem quicker because we're better at judging, oh, they're no longer connected, right? They're no longer proximate because we can measure it over finer grained characterization. You see the same same distribution here. This is the intercontact time, the time between contacts. This is how much time they spent, or inverse cumulative distribution of the time they spent in contact, which is different, 3 different studies. Now, if you look beyond how much time they spent in contact, to again focus on how does infection transmit over networks, right? Turns out that you can get very different impressions based on how precisely you measure contacts. And for those who have interests in communicable disease transmission, I recognize and respect the fact that not everyone does have those interests. But if you're interested in different pathogens like measles, which is about as contagious as pathogens get, versus COVID-19, quite contagious, flu, contagious, norovirus, also contagious. What you will see is that the attack rate, the fraction of people who are infected before the end of the simulation, for some can appear rather similar, but the variability is quite different here. There's more. It may be fair to say, I'd have to think about this some, but it may be fair to say, like with Bluetooth, where you're measuring proximity in a more precise way, it matters when one person is infected or another, whether they can transmit from A to C. It matters when they got infected. If you're coarsing grained, like aggregating up a network, or you're considering more people connected, it may be less sensitive to whether when A got infected, as to whether they can transmit to C. Here, looking at it, going from sampling every 5 minutes to every 10 minutes, every 30 minutes, every 60 minutes, every 90 minutes, 180 minutes, and this, I could say this is 3 hours, 6 hours, right? Looking for different infections, and you can see that as we start to sort of aggregate up from a really fine-grained network to a coarser-grained network, a network that treats, it is not fine-grained. It's not depicting at a very fine-grained level people's contact patterns. It does matter in terms. Also matters in terms of the attack rate and deviation in the attack rate. That's on sort of this. So for example, if you have very coarse cyst, it can lead to a lot of variability in the attack rate. That's sort of the variability from this little crosshair here, left, right. And it also has deviation interquartile range. So anyway, it turns out that, if you're measuring things quite precisely, there's less variability. You can get a lot of variability when you start to sort of coarse grain things and aggregate up. So, a sort of take home from this is that model representation of contact dynamics can lead to really significant differences in model results. And that's more true for some infections than others. But it's a good lesson that in some cases, the fact that a network is changing is actually quite important for the exact estimates you're getting out of the model. It bears on, perhaps by a factor of 2, potentially more, on, in this case, how many people are infected. As we saw, the temporal fidelity, judging by both this and this, can actually make a significant impact on the spread. And we have to be careful here. If you look at Winchell Chen's amazing dissertation on this, or the subsequent published papers, we had 2 simulations. This may be the one where we only considered 2 people to be in contact if they were present all through this time period, versus if at any point in this time period they were connected. So I'd have to go back and look for that. We considered both of them. The temporal fidelity by which we measure contacts can have a big impact on contagion dynamics. And the sampling frequency required to represent conditions varies how on the pathogen, in this case, how quickly the infection or the influence can spread within the population. So that, the provocative question that this work explored was asking, look, in this age of big data, is characterizing dynamic networks, characterizing changing contact patterns for infectious disease transmission, for communicable disease transmission, spread of pathogen, that is, transmission modeling. Is it a luxury that we have? Like, we can now collect data from smartphones or from Bluetooth beacons these days, on these contacts, and it's, it gets us extra resolution. That is just a small refinement, or is it really a necessity? And the picture that came from this, in terms of if you care a lot about estimates up to a factor of whether it's off by a factor of 2. Care a lot about who's transmitting to whom or what have you. This can be really important. It's not a luxury, it's a necessity for certain types of questions. Now, where are we going with this? Well, one big reason that one big driver for transmission dynamics, excuse me, one big driver for network dynamics, changes in network, is the fact that we have situated agents at certain locations that often induces, at any one time, they're at a certain location, any one time, that induces contact patterns, proximity networks, and the fact of mobility, the fact that people move around, whether for service-seeking reasons, affiliation, common activities, coordination needs, etc., because of interventions, the mobility drives many network dynamics. So mobility in that space. So the next sequence of lectures will turn to incorporating spatial location and mobility within ABMs. And an important thing to bear in mind here is that mobility is not, in location, is not always over a geographic space. It's not always over a regular uniform space. It may be over places that are connected with one another in some topological sense, that you can go from one place to another, where those places are treated, might represent classrooms or labs or washrooms or Tim Hortons outlets and, bus stations or whatever. And we don't get into where they are in space. We don't try to represent them in space. They may be places on different floors of the same building, and we don't seek to reason about geographic location, but instead we just characterize them as places in a network of connectivity by which they can go from one to the other, for example. So bear in mind, when we talk about situated agents, when we talk about spatial location and mobility, we're not always talking about a neat Euclidean space. We're not talking about moving on some smooth manifold. We're talking about location that could be more abstract, but still leads agents to be in proximity or not from a topological perspective. Okay, that's all we have time for today. I will head back to my office and hold office hours. Some of you will know that I've been sending out some comments on proposals, and I will continue to do that, likely tonight and over the weekend, hoping to get comments, and we'll work to try to schedule meetings to discuss projects as well. I'm going to stop this recording here and